Screen is visible. Please check.
Yeah, sir.
Yes, sir. Yes, sir.
Yes, sir.
Okay. Yesterday, I think we will start yesterday that classical free electron theory. So basics yesterday I will explain. Okay. Anyway, today we will start the first lecture one. That is session one. So there are two outcomes, SLOs. Okay. Session learning outcome, and that classical free electron theory and quantum free electron theory. Okay. But yesterday I explained what about your see basically what is atom. So how the electrons are occupied in the various orbitals and how you go to say that is valence electrons, free electrons, etc., etc. See others, please mute your mic. See others, some disturbances there. Please mute your mics. Okay. So now, okay, see now we go to start. Now that free electron theory is developed, okay, initially I think in 1900, so in the classical there are so many concepts there. So first the first classical free electron theory introduced by Rood and Lawrence. So the Rood and Lawrence in 1900 they first introduced the classical free electron theory. Okay, that is similar to the basic kinetic theory of gases. I think yesterday I told someone the kinetic theory of gases. Okay, the gas is made up of atoms or molecules, and for example, the molecules are free to rotate here and there, and so many cases you studied, so many points, the kinetic theory of gases. So now they go to follow the same. In the 1900, the Rood and Lawrence proposed the first step for the free electron theory, and they go to successfully explain and that electrical and thermal conductivity. So based on this theory, they successfully explain the electrical conductivity and the thermal conductivity. So now they go to take that is a macroscopic. What is macroscopic here? It is a macroscopic. What is the meaning of macroscopic? Microscopic. What is the difference? Anyone?
Sir, the study of comparatively large molecules is known as macroscopy, and very small, minute molecules is known as.
Yes. So macroscopic means whatever you go to see, the visible. Okay. Microscopic level. Microscopic, that is up to that microscopic level. Maybe that is invisible. Okay. The naked eye, it is not possible to see. So, and the classical free electron theory initially it gives the macroscopic theory. According to this theory, for example, here the electrons in the lattice obey the law of classical mechanics. That is, you see the Newtonian mechanics. Okay, and the electrons are moving in a constant potential. They assumed that the electrons are moving in a constant potential. I will explain one by one. Okay, what is the meaning of constant here? Periodic. The next classes you understand. So why you choose the constant potential or periodic potential like that? So this is the first step. Then again, so after 28 years, so this theory will take up to 28 years. In 1928, Sommerfeld introduced the new theory. So why they go to introduce means there are so many drawbacks in the classical free electron theory, and it could not explain. Okay, and could not explain successfully that so many concept, photoelectric effect or Compton effect or Zeeman effect. So these things are not explained by this theory. So that is a major drawback. So now in 1928, the Sommerfeld gives one more theory. So that is microscopic level. It's not a macroscopic, that is a microscopic. So here also Sommerfeld assumed that the electrons is moving in a constant potential, and it will obey the new, that is a new mechanics, that is called the quantum mechanics. It's not classical mechanics, quantum mechanics. Again, the quantum free electron theory successfully explained the drawbacks, all the drawbacks by the classical, but still it is not possible to explain some theories. That is why that the semiconductor materials behaves like this, like that. So this conducting property of semiconductor instead quantum free electron theory and band theories where the electron, for example, the electron is moving in a constant potential. So that is in the case of quantum free electron theory. But in the band theory of solids, so he said the electrons is moving in a periodic potential, not constant potential. See, so the electrons moving in a periodic potential provided by the periodicity of the crystal lattice. And it explained the mechanism. It successfully explained the mechanisms of just I told them the conductivity, semiconductivity, and the basis of these energy bands. So now you briefly discuss about both the theories, the classical and the quantum free electron theories, and what are the success and drawbacks. Success and the drawbacks. Okay, first, anyway, you attend, for example, I go to take the metal. So metal, you see the metal is composed of atoms. There's no doubt. Yesterday I told what is the meaning of atom, and the atom consists of electrons, protons, and neutrons. Okay, the electrons, there's no doubt they're revolving in the various orbits. And what about the protons and neutrons? That is in the nucleus. Okay, now the charge, electrons is a charge, negative charge, and proton is a positive charge, neutron is chargeless. Okay, so now there are two different cases are there. Okay, the positive charge nucleus, the electrons are revolving in the orbits. That condition already yesterday I told that according to Bohr's postulates, the electrons revolving in the various orbits whose angular momentum is integral multiples of nh by 2 pi. So that principal quantum number also yesterday I told what is the importance of principal quantum number, how the electrons they go to occupy under different energy levels. So now come to the theory. So according to this, so the Rood and Lawrence assumed the electrons are the gas of, for example, similar to the molecules. For example, I go to take the gas, you say that is a molecules. So here the same, for example, I go to take the metal. Okay, so now instead of molecules, that is the electrons. So see here, the free electrons of a gas of electrons. Okay, and this theory proposed by 1900, where in the 1900 they assumed that the metals is composed of large number of electrons. So you say the electron cloud or electron gas, like that, large number of electrons. Okay, and the cloud, electron cloud. Okay, now these electrons are free to move in the absence of any external electric field, or in the absence of any external field. The electrons are random orientation. So what is meant by random orientation? Yes. So what about random orientation?
Free to move anywhere.
Free to that any direction. So there is no restriction. So the electron can able to move in all the cases. Okay. Say, don't say attendance, I will take care. Yeah, please leave it. Why they are charting like this? Attendance anyway, the last attendance I will take care, please. So now, according to this, see the first in certain metals, for example, you go to see the copper and silver, aluminum. Copper is a very good conductor, I think you know, and this aluminum is also nowadays. The copper is replaced by aluminum, and almost all the cases, see a copper. What is the atomic number? Anyone? Say copper atomic number. 20?
29.
29. Okay. Silver. Ag, that is silver.
26. 47.
7. Okay. Aluminum. 1. I think.
30.
30. Okay. See, you go to see all the cases. And there's a valence electrons are there. For example, you go to take aluminum 13. Yesterday we said the sodium is 11. That is 3s1. There are 2 more electrons is there. So all the 3 electrons coming from where? That M shell. So there are 3 valence electrons is there. Okay, Al3 plus 3 valence electrons. So these valence electrons are weakly attached. That's what I'm telling. That is weakly attached to the nucleus. Now they can easily removed. That's why I'm telling yesterday that sodium chloride, how that Na sodium readily donate 1 electron to chlorine like that. Okay, or detached. Such electrons are called you say free electrons. But not all the free electrons is a metals is acting as a valence electrons is a free electrons. But anyway, and that valence electrons, the valence, for example, you go to take the valence electrons. These valence electrons behaves the free electrons here. Not all the valence electrons. Please understand. So how they go to move the here and there? Very simple. That's what I'm telling. In the absence of any external electric field, and the electrons are random orientation. It will move here and there like that. But when the field is applied, for example, external field is applied, what happens? The electrons are restricted to move. The electrons are restricted. There's no doubt the electrons are accelerated or they're accelerating and moving towards the opposite to the direction of the applied electric field, or you say that is called drifting, drifted. The electrons are drifted. You know what is the name that drift velocity? Any idea? I think you studied in the lower classes, the 12th standard. Drift velocity. Yes?
Yes, sir.
Yes. The
Yes,
electrons are drifted. That is V suffix D. That is drift velocity. Okay, like that you understand. So now the external field is applied. So these free electrons are restricted to move. Okay. So now the electrons are drifting. So this drifted electron to moving towards opposite to the direction of the applied electric field. So this movement, for example, the electrons are now disturbed. So basically, the electrons are moving here and there in the absence of electric field, random orientation. So now simply the electrons are disturbed. So from initial position to the disturbed position. So this distribution, for example, this disturbance, you say it will obey certain laws. So that is all the electrons here, the Rood and Lorentz assumed that the electrons obeys the classical law of mechanics. That is classical physics or classical law. That is Newtonian law of mechanics. Very simple, classical laws. Then based on that, they go to take the Maxwell Boltzmann distribution laws. That is the velocities identified by Maxwell Boltzmann distribution law. See here. So according to this, the metals already I told, the consist of positively ions. That is ions is fixed in the lattice, and negative ions that is very free to move in the boundaries. And these electrons are responsible for conductivity. And these electrons, for example, these could be free electrons. I say already I told, that is electron gas or electron cloud. They differ from where ordinary gas into two. First one is how these electrons is, because the gas molecules are not charged, but here the electrons is charged, negative charge. Second, the concentration of electron is far greater than the concentration of gas. Okay, there's a major difference between that electron cloud or electron gas from that gas molecules. Now they assume the following points here. See, first the possesses elastic collision. So all type of collision, already I told, the electrons moving here and there and so many cases, and each time they definitely the electron they go to collide with each other, and all the collisions are elastic. What is the meaning of elastic collision? Any idea? So why you say
There
that
is no loss of energy.
there is no loss of energy. Yes, very good. There is no loss of energy. So simply these collisions is purely elastic collisions, and the net displacement in any direction is goes to zero, and the interaction between the electron interaction is also negligible. That's what they're telling here. Between the collision is known as independent electron approximation, like that. Then how these electrons behaves in the presence of electric field. For example, up to there's no electric field, okay, the electrons move freely here and there, and they collide with each other, and you say that each collision is elastic, like that. But so what happens when some external field is applied? So that's why the electrons motion in the presence of electric field. So what happens? The same electrons, how they go to behave in the presence of some external electric field. So now definitely the electrons are not free to move. That's what I'm telling. Now the electrons are not free to move. So definitely these electrons are restricted to move. And you say that is drifted. So that concept is coming here, drifted concept. See, in the presence of electric field, so definitely the equilibrium condition is disturbed, and the free electrons acquire some the energy from the electric field. Due to that, so due to they go to get some energy from the external electric field. So again they go to move, but this time maybe the velocity goes to increase, or someone they go to lose the energy, means velocity they go to decrease, like that. So the electrons, so here accelerated. So that's why you see the accelerated and drifted. That's why I'm telling the name is drifting is coming. The net movement of electrons due to the applied electric field, you say drift, and the corresponding velocity, the electrons is moving in this drifting relation, you say that is a drift velocity, and this is accelerated towards where? Definitely it's towards always opposite to the applied electric field. Okay, as a result, due to this, the electrons occurs some velocity, constant velocity. So now you say that is a drift velocity. I think you get the expression for drift velocity in the 12th standard. Is it correct?
Minus capital
Yes,
E
sir.
tau by m.
N is by tau. Yes. Now we come to
Yes, sir.
Yes. Now come to the point. For example, the electrons are moving now. Okay. So the time taken. What is the meaning of? There are two different collision relaxation time. So the electrons is moving. Okay. Now the charge, electrons is a charge, negative charge, and proton is a positive charge. Neutron is chargeless. Okay. So now there are two different cases are there. Okay. The positive charge nucleus, the electrons are revolving in the orbits. That condition already yesterday I told that according to Bohr's postulates, the electrons revolving in the various orbits whose angular momentum is integral multiples of nh/2π. So that principal quantum number also yesterday I told what is the importance of principal quantum number, how the electrons they go to occupy under different energy levels. So now come to the theory. So according to this, so the Root and Lawrence assumed the electrons are the gas of, for example, similar to the molecules. For example, I go to take the gas, you say that is a molecules. So here the same, for example, I go to take the metal. Okay, so now instead of molecules, that is the electrons. So see here, the free electrons of a gas of electrons. Okay, and this the theory proposed by 1900, where in the 1900 they assumed that the metals is composed of large number of electrons. So you say the electron cloud or electron gas, like that, large number of electrons. Okay, and the cloud, electron cloud. Okay, now these electrons are free to move in the absence of any external electric field, or in the absence of any external field. The electrons are random orientation. So what is meant by random orientation? Yes. See, what about random orientation?
Free to move anywhere.
Free to not any direction. So there is no restriction. So the electron can able to move in all the cases. Okay. See, you don't say attendance, I will take care here. Please leave it. Why they are charting like this? Attendance anyway. The last attendance I will take care. Please. So now, according to this, see the first in certain metals. For example, you go to see the copper and silver, aluminum. Copper is a very good conductor, I think you know, and this aluminum is also nowadays. The copper is replaced with aluminum, and almost all the cases see a copper. What is the atomic number? Anyone? Say copper atomic number. 20?
29.
29. Okay. Silver. Ag, that is silver.
26. 47.
7. Okay. Aluminium. 1. I think.
13.
Go to see all the cases, and there's a valence electrons are there. For example, you go to take aluminum 13. Yesterday it says the sodium is 11. It is 3s1. There are 2 more electrons is there. So all the 3 electrons coming from where? The M shell. So there are 3 valence electrons is there. Okay, 8 plus 3 valence electrons. So these valence electrons are weakly attached. That's what I'm telling. That is weakly attached to the nucleus. Now they can easily removed. That's what I'm telling yesterday. That sodium chloride, how that Na sodium readily donate 1 electron to chlorine like that. Okay, or detached. Such electrons are called we say free electrons. But not all the free electrons is a metals is acting as a valence electrons is a free electrons. But anyway, and that valence electrons, the valence, for example, you go to take the valence electrons. These electrons, valence electrons, behaves the free electrons here. Not all the valence electrons. Please understand. So how they go to move the here and there? Very simple. That's what I'm telling. In the absence of any external electric field, and the electrons are random orientation. It will move here and there like that. But when the field is applied, for example, external field is applied, what happens? The electrons are restricted to move. The electrons are restricted. There's no doubt the electrons are accelerated, or they're accelerating and they're moving towards the opposite to the direction of the applied electric field, or you say that is called drifting, drifted. The electrons are drifted. You know what is the name? The drift velocity? Any idea? I think you studied in the lower classes. The 12th standard. Drift velocity. Yes?
Yes, sir.
Yes. The electrons are drifted. That is V suffix D. That is drift velocity. Okay, like that you understand. So now the external field is applied. So these free electrons are restricted to move. Okay. So now the electrons are drifting. So this drifted electrons moving towards opposite the direction of the applied electric field. So this movement, for example, the electrons are now disturbed. So basically the electrons are moving here and there in the absence of electric field, random orientation. So now simply the electrons are disturbed. So from initial position to the disturbed position. So this distribution, for example, this disturbance, you say it will obey certain laws. So that is all the electrons here, the Root and the Lawrence assumed that the electrons obeys the classical law of mechanics. That is classical physics or classical law. That is Newtonian law of mechanics. Very simple, classical laws. Then based on that, they are going to take the Maxwell-Boltzmann distribution laws. That is the velocities identified by Maxwell-Boltzmann distribution law. See here. So according to this, the metals already I told the consist of positively ions. That is, ions is fixed in the lattice, and negative ions, when that is very free to move in the boundaries. And these electrons are responsible for conductivity. And these electrons, for example, this could be free electrons. I say already, I told that is electron gas or electron cloud. Electron cloud. They differ from where ordinary gas into two. First one is how these electrons is, because the gas molecules are not charged, but here the electrons is charged, negative charge. Second, the concentration of electron is far greater than the concentration of gas. Okay, there's a major difference between and that electron cloud or electron gas from that gas molecules. Now they assume the following points here. See, first, the process elastic collision. So all type of collision, already told, the electrons moving here and there and so many cases, and each time they definitely the electron they go to collide with each other, and all the collisions are elastic. What is the meaning of elastic collision? Any idea? So why you say that?
There is no loss of energy.
There is no loss of energy. Yes, very good, very good. There is no loss of energy. So simply that these collisions is purely elastic collisions, and the net displacement in any direction is goes to zero, and the interaction between the electron interaction is also negligible. That's what they are telling here. Between the collision is known as independent electron approximation, like that. Then how these electrons behaves in the presence of electric field. For example, up to there's no electric field, okay, the electrons move freely here and there, and they collide with each other, and you say that each collision is elastic, like that. But so what happens when some external field is applied? So that's why the electrons motion in the presence of electric field. So what happens? The same electrons, how they go to behave in the presence of some external electric field. So now definitely the electrons are not free to move. That's what I'm telling. Now the electrons are not free to move. So definitely these electrons are restricted to move. And you say that is drifted. So that concept is coming here, drifted concept. See, the presence of electric field. So definitely the equilibrium condition is disturbed, and the free electrons acquire some the energy from the electric field. Due to that, so due to they go to get some energy from the external electric field. So again they go to move, but this time maybe the velocity goes to increase, or someone they go to loss energy, means velocity they go to decrease, like that. So the electrons, so here accelerated. So that's why you see the accelerated and drifted. That's why I'm telling the names drifting is coming. The net movement of electrons due to the applied electric field, you say drift, and the corresponding velocity, the electrons is moving in this drifting relation, you say that is a drift velocity, and this is accelerated towards where? Definitely it's towards always opposite to the applied electric field. Okay, as a result, due to this, the electrons occurs some velocity, constant velocity. So now you see that is a drift velocity. I think you get the expression for drift velocity in 12th standard. Is it correct?
Minus capital
Yes, sir.
tau by
Tau. Yes. Now we come to
Yes, sir.
Yes. Now come to the point. For example, the electrons are moving now. Okay. So the time taken. What is the meaning of? For there are two different collision relaxation time. So the electrons is moving here and there. The time taken between the two successive collisions. For example, the electrons they maybe come to a rest. For example, see here tau is the relaxation time. So how you go to take the relaxation for the two successive collisions? So the time taken by the electron for two successive collisions, you say that is a relaxation time, or you say that is a mean free time, or the collision time. It is denoted by the letter tau. Okay. So after two successive collisions, similarly the distance. So whatever the distance traveled by the electrons, for example, the distance traveled by the electrons, the two successive collisions, you say that is a mean free path. Do you understand this? I think similar to a kinetic theory of gases. Is it correct? Yes. So in the kinetic theory of gases also, you go to same. Okay. The mean free path is there. So that is the reason you go to take this one. Okay. Yes, students. Wait, there is some connectivity issue. Please wait.
Yes, sir.
Yes. I think some. Okay, I think it will come now. Yes, I'm audible now.
Yes, sir.
Yes. I think there is some disturbance, electrical disturbance here. Okay. So now, this, for example, I go to take that last session. You say the mean free path, the distance traveled, or the average distance traveled by the two successive collisions. You say that is mean free path. Or you remember this word, the mean free path? I think you studied the kinetic theory of gases. Yes. Yes. So now the electrons are assumed to achieve a thermal equilibrium after computing the drift velocity, the constant velocity. So now the electrons are comes to achieve some thermal equilibrium with their surrounding only, where through the collisions, and these collisions are assumed to be maintained in the local thermodynamic equilibrium in a particular simple way. See here, the electrons are coming. For example, how they go to identify that trajectory of electrons is given here. So, for example, it's directly coming from here the first time, and second one. So many collisions are takes place. Or in between, for example, the distance traveled or the average distance traveled by these electrons for the two successive collisions, you take that mean free path. In case of the ideal metal, so there are two, relaxation time and collision time. So the collision time, both are almost equal for ideal cases. In the case of metals, the relaxation time or mean free time is exactly, that is the reason they are telling, see here, or collision time or something. That is a tau. Okay. Are you understand this? Yes.
Yes, sir.
Okay. So now, so many points. For example, in the classical free electron theory, the first assumption is the metals is made up of atoms, and the atoms is made up of electrons and proton, neutron, etc., etc. Then the second, the positive charge nucleus is center, and negative charge electrons are revolving in the various orbits. In the absence of that external field, so these electrons are moving in the random orientation, and during that random orientation, they collide each other, and all the collisions is purely elastic. You said there is no energy loss, and they go to obey the very important. They say they go to obey a classical law of physics or classical law of mechanics, and they go to apply the Maxwell-Boltzmann distribution law, Maxwell-Boltzmann distribution. Now the electric field is in presence of the external electric field. Definitely these electrons behaves is differently. How the electrons are drifted, that's what I'm telling. That is a drift velocity, and the mean time or the average time taken for the two successive collisions, you say that is a relaxation time or collision time. For a case of ordinary metals, the relaxation time is almost equal to the collision time, and distance. Similarly, the average distance traveled by the electrons for the two successive collisions, you simply say that is mean free path, like that. So these are the assumptions made by the Rood and Lawrence for the classical free electron theory. So based on that, they go to derive the equations. They successfully explain that Ohm's law. I think you know what is a Ohm's law. Anyone? Yes. I think you studied.
V is directly proportional to I.
Yes, V is directly proportional to I.
Proportional to I.
Nice. Yeah, okay, correct. Very good. So they simply explained. I think you derived the equation also. The relation between current and drift velocity. That is I is equal to NEVD tau, like that. I think you remember. Yes.
Yes, sir.
Yes, sir.
NAVD.
Yes. So that is the NAVD. Yes, that is a N is the number of electrons per unit volume, charge of electron, VD drift velocity, the tau relaxation time, and mobility also you studied in the lower classes. So what about the electron mobility? So these things successfully explained. That is all these things coming from where? From this Rood and Lawrence theory. So they assumed the electric field is applied. So simply one kind of force is coming. That is F is equal to EE. So E is the electric field. So basically, what is that electric field? The force acting per unit charge. So simply that F is equal to E into Q. That Q is nothing but here E. That is charge of electron EE. So according to the Newton's second law, that F is equal to MA. So now you go to equate both. That MA is equal to EE, or acceleration A is equal to EE by M. So by using this A in the equation only, you get that the drift velocity, because velocity, that is the distance traveled by time taken. So here the time taken is tau. Very simple. The time taken here, the mean free time or collision time, so it is taken as tau. The distance traveled is given by the mean free path. So you go to substitute all the values, and they go to obtain some equations, certain equations. So that equation is successfully explained the electrical conductivity of the metals. And similarly, they go to develop the Weizmann France. They go to take that thermal conductivity. Both are successfully explained by this classical free electron theory. Okay, so that is a success. See, what are the success? it verifies Ohm's law. It verifies and confirms the Ohm's law, and it successfully explained the electrical and the thermal conductivity of metals. So I'm telling especially metals, not others, metals. So it will give the explanation, good explanation. That is almost they agree with the experimental results like that. Then it derives the wideband Franz law. That's what I told. That is the relation between K and sigma. That is thermal conductivity and electrical conductivity. So the K by sigma T is equal to constant. But after that experimentation, they said at low temperature, K by sigma T is not constant. That is a major drawback. Okay, not all the temperatures that is remains constant, and it is successfully explained some optical properties of metals. So these are all the advantages or success of classical free electron theory, especially that Rood and Lorentz theory that is proposed by 1900. Are you understand this? You say yes,
Yes,
or no?
sir.
Yes.
Yes, sir.
Yes. So these are the major. Okay. Now see what are the drawbacks. So same theory. Yes. Come to the drawbacks. What are the drawbacks? So the phenomena. Just I told that the photoelectric effect, the Compton effect, and the black body radiation. So and even these concept is not explained by this theory, classical theory, because that is macroscopic level. So they assumed that the electrons moving in a constant potential, and that is macroscopic. Simply they go to operate the Newtonian law of mechanics, that is classical law of mechanics. Okay, but yes, see after the class I will send the PDF in a Google Drive, no problem. See all the PPT, that PDF I will share through Google Classroom. Please you go to download and prepare for your exams. So this is that's why I'm telling. No need to take any books. You go to take this one. That is enough. Okay. Apart from this, notes also will give at the end of the each module. We will upload the notes is also in the Google Classroom. Please all of you go to download it. So now after the class today afternoon, I will upload this PDF in your GCR Google Classroom. Please you go to download it and prepare. Okay. So now the second major drawback is you cannot explain the electrical conductivity of semiconductor and insulator. See, Ohm's law is explained successfully, and the electrical and thermal conductivity of metals is explained by this theory. But the semiconductor and insulator, this theory is not explained, that's suitably explained. These two things, that electrical and thermal conductivity of semiconductor and insulators also. That is one of the major drawback. And ferromagnetism is entirely different. That is ferromagnetism is a domain theory. So that is also not explained by this classical mechanics. So why it is not explained means that assumption, because they go to assume a macroscopic level, and they said Rood and Lorentz said that is they obey the Maxwell's Boltzmann distribution something, but that is not correct, exactly correct. Okay, so these are all the drawbacks of classical mechanics. At the time of examination, they are asking in 4 mark questions. Please understand. So what are the success and drawbacks of classical free electron theory? Means at least you go to write all these points, you get 4 marks. Sometimes in big question, they are asking both classical and quantum free electron theories, or what is the major difference between classical and quantum theory, like that. Okay, so these are all the drawbacks. Any doubts here? Any doubts, please?
No, sir.
Okay, okay. So now,
No, sir.
okay, ma. Thank you, thank you. So now you move on to next quantum. So quantum, before you move on to quantum concept, I think you say the Planck's quantum theory. So he said the energy is not continuous. That is a discontinuity. Okay. So now the each, for example, the energy is a discrete format, and they go to emit it in the discrete manner, and each one you say that is a quanta of energy h nu. That concept already you know. I think you studied. So now, yes, yes. So that is microscopic level, not macroscopic level. This is microscopic level, microscopic level. So in the 1928, the Sommerfeld will come and he developed the new theory. Now, there are 2 different changes. One is, first he said the electrons are not obeying Maxwell-Boltzmann. He said that is they obeying Fermi-Dirac statistics. And second important is quantum mechanics. So these electrons obeying quantum mechanic concept and Fermi-Dirac statistics. There are 2 different. So that is Maxwell-Boltzmann.
Sir, repeat again. Repeat again.
Yes, once again. See, the Rood and Lorentz assumed the free electrons obey classical mechanics, but Sommerfeld applying quantum mechanics. Yes, understand now?
Yes.
Quantum concept, not classical. And second, so there they are telling Maxwell-Boltzmann distribution, but here they introduce a new, that is Fermi-Dirac statistics. The electrons obeys. Okay, these two concepts is different from the Lorentz and the Root Lorentz theory. So this is the quantum free electron theory. But what is the similarity between both? Both the cases, the electrons are moving in a constant potential. Please understand, whether it is a Root and Lorentz or this quantum free electron theory, the electrons are moving in a constant potential. Please understand. The only difference is whether the electrons obeying classical mechanics or quantum mechanics, or whether it is Maxwell-Boltzmann statistics or Fermi-Dirac statistics. That is the difference. But both are moving in a constant potential. That is a similarity of both the classical and the quantum free electron theory. See here, the classical free electron theory permits all the electrons to gain the energy. But same here, the quantum free electron theory, they said only the fraction of electrons gain the energy, not all the electrons, only the fraction of electrons. So now, basically you studied in the lower classes when, for example, the dual nature of light already you know. So some phenomena, the light is acting as a waves, some other phenomena, the light is acting as a particle like that. Okay, for example, you studied in the lower classes interference, diffraction, polarization, reflection, refraction. Okay, so all the phenomena, light is a form of waves or particles. Yes? Anyone?
Both, sir.
Right. No,
Dual nature.
that's okay. That's okay. I am asking that interference, diffraction, polarization, how the light is behaves.
Sir, wave nature.
Particle outside,
Wave, sir.
waves. Whether the same. For example, I go to take photoelectric effect or black body radiation.
That is particle nature.
That is
particle nature.
yes. Okay. Now come to the matter. This you say that is called dual nature. That is a dual nature of light. Okay. Sir, classes at the class up to 1 o'clock. Yes. Okay. Sorry. Faculty member. Okay. See now what about matter? Basically, the electrons as a particle. So whether the electrons behaves like say waves? Yes. Say yes or no.
Yes, sir.
Yes.
Yes.
Yes, sir.
Yes, sir.
Yes. What is the condition? So if you say yes means some condition is there. You know what is that condition? I think you studied. Okay, you'll try. No. See, basically, electrons is a particle, but the same electrons behaves like say waves. When definitely the electrons are moving, the velocity is equal to the velocity of light. So when the particle is in motion, so definitely they go to exhibit wave-like properties. That is the reason that de Broglie said matter waves. You say that is a matter waves. You studied in chemistry in I think lower classes. Yes. So de Broglie matter wave equation. Lambda is equal to h by p. So what about that lambda is the wavelength of particle. Basically, lambda is nothing but the wavelength of particle here. That is especially electrons. For example, I go to take h, Planck's constant p. That is a momentum. Or sometimes you go to write lambda is equal to h by mv because that is a product of mass and the velocity. So now, if the particle is moving in certain the electron is at rest, you say that is a particle. But the same electron moving with certain velocity v, maybe they go to exhibit wave-like properties. Are you understand this concept? Yes. Say yes or no.
Yes, sir.
Yes. Now come to the Sommerfeld. So now the Sommerfeld assumed that the electrons are obeying the quantum mechanics. Please understand the quantum mechanics. So this concept, according to quantum mechanics, moving particles has some sort of wave motion. So now the electrons are moving. For example, the electrons are revolving in the various orbits. So why not you applied that they go to exhibit wave-like properties? That is the question is given by Sommerfeld, and they go to explain. And the later, the Schrodinger developed the equation, that is a wave equation, and they introduced a new concept, that is a psi, is a wave function. So that wave function gives the wave nature of the particle, especially for electrons or something. Okay, the Schrodinger time dependent and independent wave equations, that psi is nothing but is a wave function, that is a complex quantity. So this, what is the psi? The psi is gives the details of all the details of the moving particle, especially the electrons are like that. So to characterize the moving particle, so now you introduce the wave function. So that wave function is psi. So the Heisenberg, I think you studied Heisenberg conservative principle. Yes.
Yes, sir.
Yes, sir.
Yes. So it is not possible to measure both the position and momentum.
Position momentum.
Yes. So delta x and delta px is order of h cross. That h cross is nothing but h by 2 pi. So that is a Planck's constant. H is nothing but a Planck's constant there. Okay. Anyway, you go to apply that quantum mechanics concept here. The Sommerfeld assumed the electrons obeys this quantum mechanics. And based on that only they go to select that the Fermi-Dirac statistics distribution function. Okay. Now according to this, the energy of electron, for example, the energy of electron in the nth orbit is given by n square h square by 8m L square. I think you studied in chemistry or physics, you go to derive this equation, the energy of electrons in the nth orbit. So n square h square by 8m L square, that h is Planck's constant, m mass of electron, L is the, for example, the length or the dimension of that box. So here that En is equal to n square h square by n, the energy level. For example, E is equal to 0. You say that is a ground state energy level. E is equal to 1 in the first state, second like that, E1, E2, E3, etc. So according to this, the conductivity, electric conductivity of the electron is given by sigma is equal to n E square T by m. That is a derivation. I think this is new to you, but no need to take this equation here because derivation is not necessary for you because that is a SLO. They will give only the points. So what are the different assumption and what are the drawbacks, that's all. So in case, for example, these electrons behaves like a wave and they go to according to the quantum mechanics concept. Now you got the new expression, that conductivity expression. So that is n E square tau by m. Please understand that T is nothing but a tau, that is a relaxation time, similar to that classical theory. So n E square tau by m. So n, you say that is a number here, E charge of electron, tau or D, that is a time, relaxation time. So m is the mass of electron here. So that is sigma is equal to n E square T by m. So this is a new expression and this explains successfully the Sommerfeld in the quantum free electron theory successfully explain all the drawbacks except that the semiconductor and the insulator. All the other drawbacks are successfully explained by this quantum free electron theory. See here, it successfully explained the electrical and thermal conductivity of metals as well as, but the semiconductor is slightly different and it can explain the thermionic phenomena also. The temperature dependence of conductivity also clearly explained by this theory, and it also explained some the specific heats of solids and metals and etc. etc. So these are the major advantages or the success of quantum free electron theory, but still some drawbacks is there, some drawbacks. So what is the drawbacks? So that is given here. See, it explains the specific heat of metals, it explains the magnetic susceptibility and etc. But one important drawback is, once again, is unable to explain the metallic properties of certain crystals, and similarly it is failed to give the difference between metal, semiconductors and the insulators. That is a very important, and it is not properly explained the conductive nature of semiconductors and insulator and etc. And once again it is unable to explain why the atomic rays in metallic crystals should perform certain structures only like that. So these drawbacks is completely overcome by the Bloch theory. So Bloch, that's what I'm telling, that is he introduced a new concept. What is a new concept here means the electrons are not moving in the constant potential, so that is in the periodic potential. So that is the assumption. So the Rood, Lawrence and Sommerfeld, all the three, they assumed that the electrons are moving in a constant potential. So based on that only they go to explain. But so why you not explain this semiconductor and insulator metals? Because that the theory is different. So now he said that is not a constant potential, that is periodic potential. Periodic. So periodic means, anyone? What is the meaning of periodic? Any idea?
Regularly repeated.
Yes.
Regularly repeated.
Yes. Yeah.
It's
Yes. So,
like interval of time.
yes. Okay. So that is not a constant. So that is a periodic. Maybe go to a periodically go to increase or decrease like that. So that concept is developed by Bloch. So in the same year, in the 1928, the same year, he introduced a block theory and he successfully explained. So based on that only, you said that is a band theory of solids. According to that band theory, most probably you go to classify the materials into metals, that is conductors, semiconductors and insulators. Not metals, basically here conductors, semiconductors and insulators. So according to band theory, I think you studied. So for example, you know the valence band and conduction band. If there is no gap between the valence band and conduction band and both are overlapping, valence band and conduction band are overlapping, you say that is that is
Conductor.
conductor. If the distance between the valence band conduction band is too small, so you say that is semiconductor. Yes, whether that gap, the valence band and conduction band, so the distance is too large, you say that is a insulator. So based on, yes, that is a band theory of solids. So according to the Bloch only introduced the band theory of solids, and he successfully explained this conducting nature of semiconducting materials and insulator. He said the resistivity phenomena, resistivity, conductivity. So the low resistive materials is acting as a good conductors because that sigma is equal to 1 by rho, and he successfully explained all these things. But okay, anyway, you leave that one. So now these are some drawbacks. That is the demerits of quantum free electron theory, success and drawbacks. In both the cases, whether it is classical or quantum, some advantages are there, some disadvantages also is there. Okay, so this is the first, for example, today's lecture. That is a today's lecture. You clearly understand what is the classical free electron theory and what are the assumptions for classical free electron theories, and what about quantum free electron theory, what is the major difference and what is the similarity between these two, and what are the success and drawbacks. I understand this concept. Yes, you say yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Any doubts here? Any doubts or anything else or any doubts?
No,
No, sir.
No, sir.
Okay.
No, sir.
Okay, ma. Okay. So now, okay, this is, yes, this is your first. Wait. This is the first lecture. Yeah, this is the first lecture. So that's why I go to take some periodic. Okay, whether this speed is okay for you? Yes.
Yes, sir.
Yes, I think I
Yes,
will
sir.
go to follow the same. Yes. Okay. Okay, ma. Thank you. So now it's very easy to differentiate these two because here they will give the point by points. Okay, so very simple. Simply you go to draw the table column. You go to take here one side classical theory, the other side quantum theory. So you write the difference. First, it will obey classical law of mechanics. Here quantum law of mechanics. So here you go to write. They go to follow Maxwell-Boltzmann statistics. Here the Fermi-Dirac statistics. Both are same constant potential. That is the only similarities. And so they go to approach the classical way, that is macroscopic level. So here they go to approach quantum level, that is microscopic. So they go to take that quantum mechanics. So here also they go to derive the formula, that the sigma formula, conductivity. So based on the quantum theory also you go to derive some formulas. So both are successfully explained that electrical conductivity of metals, but both the theories did not explain the conductivity of semiconductor and insulator. That is a major drawback. Why means some assumption is wrong. What is that assumption? They are assuming that both are moving in a constant potential. That is, the electrons are moving in a constant potential. So that is the wrong. So that is the case. A Bloch remodified that theory, but that Bloch is followed by the quantum mechanics only, not classical mechanics. That is quantum mechanics. Simply they go to take the electrons are not moving in the constant potential, that is in the periodic potential. Okay. I think almost all of you understand clearly, I think. Yes?
Yes, sir.
yes, sir.
Yes, sir.
Okay, no clarification. Okay, ma. So the first 3 points. So for example, here the first 3 points is given more. The why the 3 development. So classical, quantum, and that blind zones. Anyway, that blind zones you will study the 3rd and 4th lectures. Also, you go to see what is blind zones, the band theory, the Bloch theory. Also, you go to introduce in lecture 3. You go to take that KP model. So in that model, I briefly explain what is that Bloch theory. Okay, based on the theory only you go to derive that KP model. Okay, Crony-Penny model. Anyway, I will explain later. So here, introduce the electrons are moving in a periodic potential provided by the periodicity of the crystal lattice. That is an important conclusion by that block. So based on that only they go to explain. It can explain the mechanics of conductivity of and semiconductivity also. So all the cases he successfully explained by using this theory. In the same year, in the same 1928. Okay. Okay. So now I go to stop the share screen. I go to take one more screen. Please wait. Just I go to stop this. I go to share one more screen also. Just wait. Please. Okay. See, please check whether it is visible or not.
Yes, sir, it's visible. Yes, sir, it's visible.
Yes, sir.
Yes, sir.
Yes. Okay. So I think this is I don't take this one today, but anyway, I will just give some brief introduction about the densities. Okay, of states. The next class, your next lecture 2, you go to take the density. Already I told that the energy bands. Okay. Before you move on to that, so that's why I go to take this. See the energy bands. You say, for example, the electrons. Almost all the electrons in that valence band, you say that it is valence electrons or outermost electrons. See, for example, if you take the atom, the sodium, I go to take the sodium. Okay, what is the outermost electron? There is only one electron. Is it correct? Yes. See, there is only one electron in the outermost orbit. More that sodium, for example, atomic number is 11, and the configuration 1s2, 2s2, 2p6, that 3s1. Okay, so this is for one atom. One atom. For example, I go to take Avogadro number of atoms. For example, you say that is a 1 mole of any gas contains Avogadro number of molecules or atoms like that. For example, I go to take such a 1 gram of sodium. How many atoms are available? 10 power 23. The Avogadro number is
523.
6.023 into 10 power 23. So the 10 power 23 atoms. So each atom, there is only one electron in the outermost orbital. Are you understand this? Each atom. So now 10 power 23 atoms are there. So how many free electrons are available now? Tell me.
10 to the power 23.
10 power 23 number of free electrons are available. Are you understand my concept? What I am telling? Please.
Yes, sir.
Yes. See, there are 10 power 23 such atoms, and there are 10 power 23 electrons are available. Okay. If you don't remember the 10 power 23, for example, I go to assume that 1000 electrons is there in the valence. Okay. So now almost all the cases, this you say that is valence band. You say that is a valence band. Then just above the valence band, the empty band is there. You say that is a conduction band. I think that is called a conduction band. The normal room temperature, some only the few electrons only moving from where? From the valence band to conduction band, because the electrons are coming from where? Lower energy level to higher energy level. It is not possible. Okay, without help of any external agency, it is not possible. The electrons are moving from that lower energy level to higher. Is it correct? Yes.
Yes, sir.
Yes. But anyway, few electrons, for example, the normal room temperature also in the semiconductors, the few electrons are coming from where? The valence band to conduction band, not all the electrons. So that time they go to create the holes in the valence band. So I think you know that the whole electron concept. So electron both are charge carriers. There is no doubt. So electrons is a negative charge, is a charge carrier. Holes, that is a positive charge. That is also a charge carrier. Both electrons and holes. Now your next lecture, for example, lecture 2, you derive the equation. So that is very important derivation. So you go to take the density of states. So that is energy bands in solid, density of states and energy bands in solids. So now you clearly understand what is the energy band. So for example, all the valence electrons they go to come. What you say that is a valence energy gap or valence band and a conduction band. So you say that is a band theory. All the lower levels are completely filled. But what about the higher energy levels? Almost empty. So now how you go to take this one? And what are the how many available bands or what are the available states is in that energy band? So that only you go to derive in the next class. Okay. So now you clear, for example, that diagram is visible for you. Please check.
Yes, sir.
Yes, some basic I go to take today because this is a derivation. It's not easy to understand. That is the reason I go to take this. See, in this diagram, you go to see here. I go to take the two energy levels. The two energy levels, that is completely filled. For example, that case say here, and the find the number of energy levels in the cubical metal piece to find the number of electrons that can be filled in the given energy level. Okay, so our aim is go to calculate how many number of electrons, that is the number of electrons that can be filled in a given energy level. So now I go to take two energy levels. So that is A and E plus D. See here, the two energy levels I go to consider, that is E. That one energy level is E. The next one is E plus D. So what about our aim is the number of energy states between these two energy levels, E and E plus D, found by finding the number of energy states. Please understand that is the number of states or number of energy states between the two energy levels E and DE and the radius of N and N plus Dn or delta N. So I go to take the radius here. For example, this is a cubical structure and this is a midpoint is O. Okay, this is along x direction. I go to take this length nx, ny, nz, all the three dimensions. So now I go to select the two energy levels. See here, the one energy level is E, the other one is E plus D. See the diagram. So here that is E plus D. My outer cell is E plus DE. My inner one is E. And similarly, the distance N and N plus delta N. See the distance between the two energy levels E and E plus DE is given by delta N. Delta N. Okay. Let us construct the sphere of radius N. So radius is nothing but radius of the sphere is nothing but N. You say that is a distance. That is a distance. I understand this. Yes.
Yes, sir.
Yes, sir.
Yes. Okay. So now you clearly understand that E and E plus D is the two energy levels, and N is the radius of the circle, and the distance between what is the distance between the two energy levels here?
Delta N.
Delta N. So from the diagram, so please understand. That's why I'm taking. You see the diagram. So that is delta N. That is delta N. Now our aim is finding the number of the available energy states, the energy states between the cells L and the N plus delta N distance. So N is nothing but a radius, and N plus delta N is the distance between the two energy levels. Okay, the volume of the sphere already I think you know. So what is the volume of the sphere? 4 by 3
Pi r cube.
so instead of R, I go to take it here N because I assume the radius is N. So that's why I go to take that is 4 by 3 pi N cube. Instead of R, I go to take N here. Okay, that my assumption is N here. And similarly, there are N three dimensions. I go to take that Nx, Ny, Ns, all the three dimensions. See here, Nx, Ny, Nz, all the three dimensions is there. Okay, so based on this, you go to derive the equation. So that derivation we will discuss in the next week. But anyway, now you get some idea. So what is the meaning of the density of states? How you go to calculate that number of energy states between the two energy levels. If you go to find out the two energy levels, and very easy to say that the entire energy level, simply you go to integrate with certain limits. Correct? Yes. Integrations or summation, whatever. Okay, you go to C. So that is a final equation. On the final equation, you see what is the density of available number of states or number of energy states. Yes. Are you understand?
Yes, sir.
Yes. Okay. Anyway, this is the next class only. But anyway, I will give some introduction here. That's all. Okay. Okay, ma. I think I just wait. Okay, so any clarifications here? Yeah, any doubts today's class? Any clarifications or doubts? Anything? No.